Assalamualaikum and hi, I bid to Dr. Ibrahim and all my fellow classmates. We are from Group 4, which consists of 3 members. I will introduce myself first. My name is Nurul Hanis Bendana Zamri with metric number 208253, and next I will pass to Hanif.
Thank you to Hanis. Okay, my name is Muhammad Hanif bin Muhammad Dom. My metric number is 06406. Next, I will pass to Shasha.
Hi, I'm the last member. My name is Nur Shanshayura binti Mazlan and my metric number is 207208. Next, I will pass to Hanis.
Okay, so let's proceed to our slide presentation. Okay, so our group will present about the electronic, optical, and magnetic properties of the lanthanoids. Lanthanides. Lanthanides are the rare earth elements of the modern periodic table, which the elements with the atomic number from 57 to 71. The valence electrons of these elements lie in the 4f orbital except for the lanthanum. So as you guys can see, these are all the lanthanide series from cerium to lutetium. And the table of contents of our presentation today is, firstly, electronic absorption spectra, secondly is optical, and lastly magnetic properties. Next, I will pass to Hanif to explain more about electronic absorption spectra.
Alright, thank you to our host, which is Hanis. Okay, today I'm gonna explain about electronic absorption spectra. It is obtained by measuring the amount of radiation absorbed by a sample as a function of wavelength of incident radiation, which reflects the electronic degree of freedom of an atom or molecule. Next slide. Okay, transition only involve a redistribution of electrons within 4f orbital or FF transition. It is pale in color. Crystal field effect for the lanthanide 4f orbitals are virtually insignificant, unlike transition metal complexes. This is a result of the extensive shielding of the 4f electrons by the 5s and 5p orbitals. The FF absorption bands are very sharp. Okay, there is 91 microstate of FF transition. The electronic state and spectra can be discussed in the free ion limit and the Russell-Saunders coupling scheme despite the elements having high atomic number. The large number of microstate means a correspondingly large number of terms, hence, large number of possible transition between them. As the terms are derived almost purely from f orbitals, there is also little d f orbital mixing or mixing with ligand orbital that made the transition Laporte forbidden. Electron in 4f orbital interact weakly with ligands, so there is a little coupling of electronic transition with molecular vibration. Hence, the bands are narrow and gain a little intensity from vibronic coupling. Next slide. Okay, there is two spectrum, which is lanthanide spectra and d element spectra. You guys can see lanthanide spectra are very sharp and strong, but the d element spectra are broad. Next slide. Okay, there's the end of my presentation. So I will end with this joke. Don't drink water while study because chemistry say that concentration decrease on aiding water. Thank you. Next, I will pass to next presenter.
Thank you, Hanif. That's a very good explanation for electronic properties. So, thank you, Hanif. That's a very good explanation for electronic properties. So I'll proceed to the next table content, which is optical. Optical studies provides informative data on the structure of electronic energy band spectra of rare earth metals, as well as the kinetic properties of carriers. Lanthanoid ions show useful emission spectra with applied ions in phosphorus, lasers, and imaging. It is derived from their emission spectra produced after excitation of the F electrons using energetic photons or electron beams. There are two types of emission. Firstly is fluorescence and secondly is phosphorescence. Fluorescence is from a high energy to a lower energy state having the same multiplicity, spin multiplicity, which is delta S equal to 0. In other words, that if the two emitting and receiving levels have the same spin, the process is being allowed and it is a pulse. Thus, it's called fluorescence. Secondly is phosphorescence, the longer-lived transition from a high energy to lower with different spin multiplicity, which is delta S not equal to 0. In other words, emitting levels has different spin than the receiving levels, so it is a spin forbidden. So it is slower. Thus, it's called phosphorescent. Next, all the lanthanoids except lithium 3 plus and lutetium 3 plus show inherent luminescence. The strongest and the most useful emissions are europium 3 plus and terbium 3 plus. Europium 3 plus, which is quintet D0 to septet F0 to 6, which giving the rate, and terbium 3 plus quintet D4 to septet F0 to 6, giving green. It is due to large number of excited states that exist, thus increases the probability of intersystem crossing and lead to rising phosphorescence. The strength of emission stems from excited electron interact with only weak lead to long non-radiative lifetime. As you can see on the left diagram, which is simplified energy level diagram for lanthanoid trivalent cations. Here is for europium and this is for terbium. For europium, there are so many emission from the D to F orbital. Same goes to terbium from D to F orbital. There are so many emission. Next, we proceed to luminescence. Natural emission is limited that the excitation by absorption is only weakly allowed. Thus, luminescence can be enhanced by placing antenna on the ligand in a complex or nearby in a solid material. The antenna is excited by a Lord transition and energy is transformed either directly or indirectly via, via IC into excited states of lanthanoids. The processes are represented by Jablonski diagram. As you can see at the right diagram, uh, there are Jablonski diagrams. So this is the enhanced emission, and this is the ground state, and this is the antenna. Next is electroluminescence. Lanthanoid compounds are excited electrochemically by using electrodes to inject electrons into their higher orbitals of suitable organic groups, then remove the electrons from the occupied orbitals. Do you know that iPhone have an organic light emitting diode screen, or the short name for it is OLED, OLED. OLED emits light when an electric current passes through it. OLED screen does not need a big or black light because the pixels light up on their own, so much more power efficient. That's all from the optical properties. I'll pass to Shasha to explain more about the magnetic properties.
Next, I'll be explaining about the magnetic properties. The core-like nature of the unpaired 4f electron in lanthanoid compound lead them to exhibit magnetic moment in close agreement with the values predicted for the free ion based on the Russell Saunders coupling. Next. The magnetic properties are basically determined by the 4f electron, which are well shielded by the occupied outer shell of 5s and 5p electron. The magnetic field are generated by the unpaired electron aligned and spin in the same direction. There are two types of substance, which are the paramagnetic substances and also diamagnetic substances. The paramagnetic substances, which are attracted by the magnetic field, and paramagnetism is caused by the presence of the unpaired electron, while the diamagnetic substance is the substance which are repelled by the magnetic field, and the diamagnetism is caused by the presence of paired electron. Next. So basically, this is the magnetic moment value for the lanthanoid series. So as you can see on the table, the LA and also the LU3 plus and LA3 plus is 0 because they are diamagnetic substances. Next. The LA3 plus is a 4F0 and LU3 plus is the 4F14. So they have no unpaired electron. The electron configuration is 5d1 and 6s2. So when LA lose 3 electron, it becomes LA3 plus and there will be no unpaired electron. Thus, they do not show the paramagnetism, while all other trivalent ions of lanthanides are paramagnetic. The magnitude of the paramagnetism of a substance or ion is commonly reported in the term of the magnetic dipole moment it possesses, which the higher the magnetic dipole moment of the complex, the greater the paramagnetism. Magnetic moment of the lanthanide ions are generally described from the coupling of the spin and orbital angular momentum, which the Russell-Sander coupling scheme. The magnetic moment mu is expressed in terms of the total angular momentum quantum number G. So as we can see, this is the formula where the mu B is the Bohr magneton and G is the total of electronic angular momentum. Next. This is the Landé G factor based on the previous formula, which has been described into this Landé G factor, where L is the total orbital angular momentum and S is the spin angular momentum. The spin or orbital coupling is stronger than the ligand field splitting. Then the orbital angular momentum contribute to the magnetic moment and the ions behave like the almost free ion. Thus, the magnetism is essentially independent of the chemical environment. I think that's all from our group. And don't forget to join the bike race that will be conducted in the class. Thank you.